I got it! I got it! I got this harmless weather instrument. Shot a hole straight through it, guys. It's pretty epic. Anyway, we're here to learn about Kepler's laws of planetary motion right now. So you should open up your notes packet to the part where it says Kepler's laws of planetary motion. Kepler's first law, which you should write down, is planets move in elliptical orbits. So really mostly what this law is going to be about is ellipses, like the geometry of ellipses. Okay, so if you're like, well, I learned a little bit about those in geometry class. Yes, you did. Most of the features of ellipses that you probably learned about, though, aren't that relevant for physics. Okay, so pretty much I'm going to teach you only the parts about elliptical geometry that matter for doing physics. So here's an ellipse, roughly speaking. The names of the various axes are as follows. The whole way across is called the major axis. All right, that's the long way across. If we're going the short way across, that's called the minor axis. Really, neither one of those exactly matters all that much. The part that actually matters the most when you're looking at an ellipse is the semi-major axis, as it is called. Okay, I'm going to erase so that I have enough room to put in. Here we go. The semi-major axis is represented by the letter A. And it's sort of, if you like, analogous to a radius. So it's kind of sort of like radius is to diameter as semi-major axis is to major axis, right? A radius is half the diameter of the circle. The semi-major axis is halfway of the long way across an ellipse. All right, there were two other points on here that I'm going to focus on. Pun intended, probably. Okay, those two are called the foci or foci. I will usually say foci, but whatever. It's the plural of focus. An ellipse has two such foci. Technically, a circle is actually an ellipse where the two foci happen to be in the exact same spot. So a circle has one focus because it's a special ellipse where the foci are in the same spot. Okay, all right. So two foci, semi-major axis. All right, that's the important bit for this diagram. Now, next thing is the sun is always at one focus of the ellipse. The other one is nowhere special. So as the planet goes around the sun, there's going to be one point where it is closest to the sun and another point where it is furthest away from the sun. Where it is closest is referred to as perihelion. And over here where it's furthest away is referred to as aphelion. All right, there are analogous positions for things that are orbiting around the Earth. So, for example, the moon has a position that's called perigee. That's when the moon is closest to the Earth. Apogee is when it is furthest away from the Earth. All right, so the prefixes peri and ap refer to closest and furthest away. All right, now it's also worth noting that the seasons of the Earth are not due to perihelion and aphelion. All right, it's not like we have winter because we're further away from the sun during winter. I don't even know if that's true. It has to do with the tilt of the Earth's axis. All right, so don't imagine that it's because of being closer or further away. Really, the Earth's orbit is quite nearly circular, so the differences in distance don't matter all that much for us in terms of the amount of heat that we receive from the sun on a daily basis. Okay, so seasons have nothing to do with this. However, perihelion and aphelion do relate to one other thing, which is the speed of the planet. I'm technically jumping ahead a little bit to Kepler's second law when I talk about the speed, but I want to prepare you for that one just a little bit, even though it's only like 30 seconds away. as something orbits around the sun, when it's, let's start here, where it's far away, right? Drifting, around in space, kind of pretty slow. Oh, but there's the sun. It's going to pull it in, and as it pulls it in, you can imagine it's going to go faster and faster and faster and whip around and then slow down, because the sun's pulling it towards itself still, right? So it's slowing down, just like if you throw a rock up in the air, right? It's going to slow down as it moves away from the Earth, all right? And then repeat that process over and over. So slowest when it's furthest away, fastest when it's closest to the sun. That's true for any orbit of anything around anything at all, as long as it's elliptical. All right. A little while ago, I think a little while ago we learned an equation for the speed of something that's moving in a circular orbit. That equation does not apply to ellipses at all, so I won't even write it down, okay? Anything at all that has to do with circles does not apply to ellipses. As this thing's moving in the elliptical orbit, it's speeding up and slowing down. Things moving in circular orbits don't do that. They have a constant speed because they have a constant distance away from the thing that's in the center of the orbit. So the speed won't change unless there's like some third planetary body out there that's acting on it and messing with its orbit. It should be constant. Okay. That is everything that I think we need to know about Kepler's first law. Kepler's second law. Kepler's second law is super wordy, so I wrote it down just the way he would have said it, and then we'll visually explain what it means, and then I'll tell you what it really means. Okay, so he says a radial vector, all right, drawn from the sun to a planet. All right, let's pause there for a moment. A radial vector really is just a straight line drawn between two things. So a radial vector drawn from the sun to a planet would just be a straight line drawn from the sun to the planet. There it is. All right. Sweeps out equal areas in equal time intervals. Okay, so in terms of sweeping out an area and over a time interval, here's what he's talking about. Let's say day 1, the planet is here. And then you check back on day 31, 30 days later, and the planet is here. What Kepler's talking about is if we draw that radial vector, again, and then we look at the area of this sort of pie-shaped slice thing here. Right? Whatever that is, let's call it A1. Right? That's a certain amount of area swept out by that radial vector that we just drew. All right. Now let's look at the planet when it's in a different place, and then over a similar time interval. So way over here, let's say on day 100, the planet, whatever it is, just happens to reach aphelion on day 100. I picked perihelion and aphelion because drawing lines is easier for those two spots, but whatever. All right, radial vector drawn to it. I missed. All right, at day 100, there it is. All right. 30 days later, the planet is here. That area is, it looks very differently proportioned, but what Kepler was able to show by very, very careful measurements and calculation and so much geometry was that this area is exactly the same as the other one. As long as you're looking at the same time interval, that radial vector drawn between the planet and the sun is always going to sweep out exactly the same amount of area. All right, so that's kind of a crazy thought right there. But also, what does it really mean? What is Kepler trying to say by this? All right, now, I don't know exactly what Kepler's conclusion was from this, but I think what his conclusion should be is what we now take from it, and probably this is what he was going at too, is that the velocity and the radius are inversely proportional according to this equation right here, which you should definitely write down. All right, now it's not actually quite that. I'm simplifying a little bit. That's only true as long as we're looking at perihelion versus aphelion. Other places we have to worry about angles, because more technically it's involves something called a cross product that we may or may not have learned about at this point yet. Okay? So yeah, we may or may not have learned about cross products yet, and so you might not be able to deal with other positions, such as like right here. But fortunately, I also won't ask about those. The only two spots that I will ever ask about for comparing speeds and distance from the sun are going to be perihelion and aphelion. And in that case, this equation works just fine. So all it's really saying is that as the radius, the distance from the sun, increases, the speed goes down. I know I already said that over there on that other board, but this was how Kepler was able to demonstrate that the speed changes, right? The only way that the areas could be the same, even given how long these are compared to those, is if it's moving faster here, covering more distance, and slower out there, covering less. All right. Next thing would be we're going to prove Kepler's third law. So go ahead and find example, I think it's example 3 in your notes packet. Yeah, it says derive Kepler's third law for a circular orbit. All right. Kepler's third law says the following. I'll just write it down. All right, now what Kepler's talking about in this one is the period in seconds, mind you, squared is proportional to the semi-major axis cubed. This is not acceleration. Not acceleration. It is the semi-major axis, and it is cubed. All right, there's a lot of things calculationally to mess up here. Now, what we're going to try and do is prove this for a circular orbit. So notice I put or r cubed, because if it's a circular orbit, the radius is the semi-major axis. So I'm going to write down the two equations that you need, and then you're going to derive it from there. Okay, so you can pause the video after I write down the equations, and then see if you can derive it. And if you get stuck, then resume and look at my work. So one thing would be this. If it's going in a circular orbit, we've said before that the period would be equal to the circumference divided by the orbital speed. All right, second thing is we need an expression for the orbital speed. So the orbital speed we got from saying, well, if it's in a circular orbit, then the gravitational force provides the centripetal force that keeps it in a circle. So gmm over r squared equals mv squared over r. From this and this, you should be able to get that. All right, so pause the video and try and do that. And if you get stuck or you just want to see if you did it right, resume. And there it is. Squared both sides. Solve for v squared. Plugged it in. And go from there. All right, stay tuned for the next video.